All right, so this one is fairly easy to see. We just basically, anytime we get a positive number out of our function, it becomes negative. Anytime we have a negative number, it becomes positive. And so it's like you put a mirror right on that x-axis and you're looking at it and you see the reflection where what's above is now below. So if we were to take the function and put a negative in it, with the absolute value, remember, if we're looking at trying to make a horizontal reflection, the absolute value would look exactly the same, right? You would turn it around and you couldn't tell if it was the reflection or not. So I'm choosing the square root function because the square root basically starts at 0 and it goes off to the right. Now, we have a domain issue because if I were to take the negative x, then it doesn't evaluate for positive values of x. So I'm going to extend this table that says, okay, let's take x from 4 to negative 4, and I know that f at x doesn't evaluate at negative 1 and negative 4, and g at x doesn't evaluate at 4 and negative 4. But if I were to graph that, what I would get is first f at x would go off to the right, and then g at x would be its mirror image going off to the left. Left, right? Yes?
Sorry. I thought having the negative x inside a square root was like super legal.
It is.
Okay.
And negative 4 is 4, so the square root works just fine. So what you're getting at is that if we have this value, the square root of x, then x has to be greater than 0, okay, or equal to 0. Now, if I have this thing negative, let's say, I'll put another variable in here, let's say negative z, what has to happen is that negative z has to be greater than or equal to 0. So in this case, then, z would be less than or equal to 0. So the domain is different, or the values, the permissible values of z are different because you have the negative. It's this expression that's inside the square root that has to be greater than or equal to 0.
Now, it's okay because we're not saying negative, we're saying the opposite.
Exactly,
Okay,
exactly. So,
that's right.
yeah, negative 4 is positive, so you're within the domain of that function. There was another question somebody had? No? Okay. So when we make the argument inside of a function negative, what we get is a horizontal reflection of the function. And so if you have a symmetric function, of course, this doesn't change. So the function f at x squared, or f at x equals x squared, if you make x negative, it doesn't change, right? Because you still have just x squared. And so you turn your parabola around, and you get exactly where you started from. So we do have some words to describe this. So with the function f at x equals x squared, if you put a negative in there, it evaluates right to itself. If we have a function like x cubed, where the negative can go out, where the function retains the negative sign of that x, then we get g at negative x equals negative g at x. Okay, so here's a little different behavior between x squared and x cubed. So just to draw that, you can see in the first graph, rotated about the x-axis or the y-axis, and you get exactly the same thing. But if I were to take g at x and rotate it about the y-axis, of course, it turned out to be something quite different. And so we have a word for this. If f at x equals f at negative x, then we call this an even function. And if negative f at x equals f at negative x, then f is an odd function. Now, if you're like me, you always look for different ways to remember things, because just outright memorization is hard after a while. My brain is too old and cluttered to remember things like this. So the way I remember it is that I understand what x squared will do. If I make it a negative x, I'll get the same function out. the squared, the 2 in there is even, so that's an even function. If it behaves like x squared, it's an even function. If it behaves like x cubed, in the sense that the negative x would give you the negative value of the function, that's an odd function. So even and odd. So we can have a function that can be even, odd. Most functions that you come up with are neither, but you can't be both even and odd. So that's the thing that that's not possible to do. But it's possible, of course, to be neither. Okay, so the absolute value of x, is that an even function or is that an odd function? What do you think? It would be even, right? Because you'd make a horizontal reflection and you get exactly the same thing. How about just f at x equals x? It's odd, right? Because when you think about what the graph looks like, you just have a diagonal line going right through the origin here. We make a horizontal reflection, and it goes like this. And so if this is f at x equals x, then this is f at negative x. So that's going to equal this function here. Okay, we good? You up to it?
So are all odd functions one-to-one functions, and all even functions are basically where there's like x can have two different or two of the same lines?
Yes. It's not necessary to be either even or odd and be one-to-one. You can construct examples both ways. For example, f at a constant is an odd function, but it's not necessarily a one-to-one function because you have many values of c for any value of x, or no, for any value of x you get just c. So it's not one-to-one, but it's certainly an odd function. While f at x, of course, is an odd function, but it is one-to-one. But it's good to think about functions like that. You know, all the things that you use to characterize a function, look at that in those ways. Is it possible to be one or both or neither? Things of that sort. So I'd like to take a few minutes, and I'd like you to make this graph, and I'm sure it'll take about 5 minutes or so. So just please, try and do this real carefully. What I'm asking you to do is make up a table or something like that where you're going to make the graph 4x minus x squared, go from 0 to 4. So the values that you would use, we can use integers here, so use 0, 1, 2, 3, and 4. So evaluate f at x at all those and then graph it. And I'll give you a preview of what that looks like. It's going to look like this. Okay, so it's an upside down parabola, and it's going to have its maximum value at 2, and it's going to go back to 0 at 4. So I'd like you to then take that function and multiply it by 2 or multiply x by 2 and graph it in those intervals and see what we come up with. All right, any questions on this? So we have this rule of expansion in height and in width, and then we have rules earlier for how to move, say, the vertex left and right, up and down. So we can combine these things to be to have a general set of rules. But let me first kind of articulate or recap what we had here. So if we have this function that we multiply by a constant, it's going to stretch it vertically. If it's less than 1, it's going to compress the graph. And if it's less than 0, remember when we have that negative in there, we get a vertical reflection. So it's possible not only to make the reflection, but to also either stretch or shrink it if k has a value other than 1. So what we did before when we just put a negative sign out front was we were multiplying it by -1. Now if we put any other value around that, let's say -2 or -4, then you can get that stretching coupled with the reflection. And then if we put something, if we multiply the variable by a constant before we evaluate the function, then here what happens is kind of the opposite of what you would think. If you multiply it by a number greater than 1, it compresses the graph, while if you multiply it something less than 1, it stretches the graph. And that's one of the reasons why I had you make this table and do the graph, is so you can actually get a feel for what's happening here. That when this 2x, this f at 2x, it actually goes through the whole cycle but in a more compressed fashion. So when x equals 2, then this is going to be f at 4. And so really what it's doing is it's kind of changing the scale of your x-axis more than anything else. And of course, if k is less than 1, or less than 0, you can get the horizontal reflection that we had when we made f at -x. We can also scale it at the same time. Okay, was there a question?
Can you go back?
Sure. Okay, going to move forward here. So let's throw it all together and let's make a graph of this function. And this thing looks, well, it looks a little vaguely like one of our toolkit functions, but it has so many things going on with it. What would it look like? Okay, we have an instance where we have this variable x that's in the denominator, and that expression that involves x is squared. So the toolkit function that we probably should start with is 1 over x squared. Now how do we kind of unpack this thing to decide what's going to happen? So once we decide what toolkit function we're going to use, the first thing that we do is we say, okay, let's take -3 times that toolkit function, and so we get -3 over x squared. So we get this vertical reflection. So remember what 1 over x squared looks like. I'll draw it on the board here so you can keep it in mind. It looks like this. And so this thing is going to then make a vertical reflection, so it's going to be upside down, and it's going to stretch it. And with this particular graph, unless you start putting numbers on the graph, it's hard to see the stretch. So we'll just kind of understand that we do have a stretch involved here. Then the next thing that we do is, okay, we don't have x, we have x minus 1. And so we say, all right, let's take x minus 1, and what we get then is a right shift of 1, right? When we have that x minus h was the expression, it goes to the right by h units with that negative sign, so we're going to expect that this thing, already upside down, is going to shift to the right by 1. And so then the only thing that remains is to add 2, and adding 2 is the easiest thing to do, right? Because all we're doing is we're moving it up and down, and so we're going to move it up by 2. And so imagine this thing now. We have this upside down. we have it over 1, and it's going to be up 2. And so there's the original graph. The one that we would come up with is something like this, where it would be upside down. And you see where the origin is? It's right here. That's kind of there. What I've done is by drawing these dashed lines at 1, where x equals 1 and y equals 2, that kind of gives me kind of the center of interest, or the midpoint of the graph in some fashion. That's the point that we're taking and moving around. So everything is with respect to that one point that used to be the origin, that now has that kind of maybe main focus of the graph.
Aren't we supposed to stretch it by 3?
Yes, and there's really no good way to stretch it without putting numbers on it.
Got it, okay.
So imagine this thing stretched with my lousy graph, it'd look just the same. So it'll be different in some other graphs where it'll be a little easier to tell. Like with a parabola, it's easy to stretch it because you just make a wider one. This one, like I said, we have to put numbers on there to really get something. Okay, so that's the end of section 1.5.